So if we take a look on this page, this is a quick reference. Um, you know aliphatic versus arenes and saturated versus unsaturated. Did Mr. Verbrugge talk to you about electrophiles?
No.
Okay, so then you will want to get this definition down. So basically electrophiles are positive parts and they are seeking electrons. So they are electron deficient, so they're searching for it. The opposite of this is a nucleophile. Nucleophiles are basically positive seeking things because they have all of their electrons. So I think hopefully you can see that.
I mean, I have the textbook with me as well.
Oh, okay, cool. So those are the key things. Now, if we take a look, these types of reactions are what we're going to be dealing with, and that's just below that. It talks about the addition, substitution, and then addition, elimination reactions. Those are kind of quick things. And then it also talks about homolytic fission, heterolytic fission. So homolytic fission makes two things that are the same. In this case, radicals of X. And heterolytic fission makes one that is positive and one that is negative because it ends up taking all the electrons.
What's a radical?
Basically, it's something that is free. It has, as you can see, one electron. It's unpaired.
Okay.
So basically, it something that's does not last very long. Then it has a convention for writing these, and this is an optional thing for standard level. But if you can see, we have basically electrons. We're kind of showing them with a curly arrow. So this is kind of showing the bonding electrons going to the Y. So that would be like a heterolytic fission where Y has all the electrons of that bond. And here we have a nucleophile. Remember, it has these electrons and it's searching for a positive place. So we're showing an arrow here to show that that's where it's going to be attracted.
Cool.
All right. So that brings us to the substitution reactions of alkanes. So, you know, alkanes can undergo combustion. That's an easy one, right? So if we have an alkane, let's just do methane for ease. We can add that to oxygen and that will make carbon dioxide and water for complete combustion. Right?
Yeah.
If we don't have an abundance source of oxygen, then this could also make carbon monoxide and water. That's like the fear of in your house, if your heating element, like if you have a gas heated house and you don't have enough oxygen supply, then that could start basically producing carbon monoxide inside your house, and then you could suffocate and die. That's why people have, if they heat by gas, they have what's called a monoxide detector, right?
I do not have a monoxide detector.
Do you have? You probably don't heat by gas, do you?
Probably have. Well, I know our stove is gas.
Oh, maybe you do have gas heating. So that's one reaction that alkanes can go through. Apart from combustion, the only other reaction that alkanes can go through is called halogenation. Right? Halogenation. But if we take a look, basically just break down the word. Basically, we're adding a halogen. Now, this reaction cannot occur in the dark. it needs the presence of UV. Now, these notes have UV here for ultraviolet light. You may also see Planck's constant and nu. And that's basically just saying in electromagnetic radiation, right? Do you remember the wave reaction? The electron, the energy of the photon equals h times frequency.
Sounds familiar.
Yeah. So basically, what you would see is that they're taking the Planck's constant, and they have this looks like a V, but it's a mu. And basically, that you could see those either one of these. I'm just telling you that because in the test or in the book, you may see it as HV or H mu, really. But that's the only thing. I'm just letting you know that that could be an example. If you're doing this reaction, you have to have this. If this is an alkane, this has to be put up there because it cannot happen in the dark. So that that ultraviolet light will cause the chlorine here to form free radicals through homolytic fission. And we can have then one of these H's become substituted by one of those free radicals. The other part of the free radical could merge with that H that came off of there. We can do this on larger chains as well, and we can do it with other halogens. In this case, the ultraviolet light would make 2 bromine radicals.
So it essentially like creates an acid?
Well, I mean, it creates a halo alkane. And I see what you're saying. And this acid, yep, that would also be created. Sorry, I was more focused on this part. Yes.
I don't know. I just saw the H and I was thinking.
Yep, you're exactly right. I mean, with this organic part, I was more focused on the organic parts of it. But yes, those are also there. So if we take a look, then what most of the tests, the paper 2s have you do is write out basically one of these reactions. And what you need to do for full credit on that is you need to write out and explain and describe the reaction mechanism. So again, that we have this is called free radical substitution because we're making these free radicals out of the chlorine. And as we said, they don't last long and they're highly energetic and reactive. So again, this goes through what that one page did. It shows you the heterolytic and the homolytic fission. This is the part that's going to suck because basically you'll just have to memorize this type of setup and then be able to do it with whatever compounds they give you. And what they would do is maybe instead of giving you methane, they give you ethane. And instead of chlorine, they give you bromine, right? So the first step is known as the initiation step. That is the radicalization of the chlorine by using the ultraviolet light. And then you would just write this as this with 1 dot because it has that extra electron from
free radical.
This free radical. There you go. The next step is propagation. That free radical then comes in, and as you said, it pulls one of these hydrogens off of here, making that carbocation we were talking about before. Or actually, no, this isn't a carbocation. This is actually a radical of methane. And then HCl. So that's the first step of the propagation. Now that we have this being a free radical as well, this can pull off one of these chlorines and make your methyl chloride. And then we have another free radical here. So what can this free radical do then? Well, that one can go back and pull off another hydrogen. Or it could pair up with a chlorine, and that would stop it. And that's what we call a termination step. So we have this, which is propagation, which forms another free radical, and this propagation, which forms another free radical. We have possible terminations. These two free radicals come together. These two free radicals come together and we get what we want probably. This is probably what we're trying to make. We could be trying to make this though. We could be trying to make this. And that would be done from two of these free radicals coming together. So basically you start with one thing, that one thing propagates another thing, and then basically you have two things going out there, two different types of radicals, and then you have to pair them up with themselves, and then pair them up with each other. Notice
Is there a particular reason that the UV causes the chlorine to up?
to form the free radical.
Yeah.
So UV light causes the bonds to kind of torque and stretch and twist. And this is just one of those cases of where it ends up causing the formation of the free radical. UV light can cause those changes. And I think whenever we get to the NMR and stuff like that, we'll talk more about how that UV light affects it, because there are, like, you can take readings from that and actually, you know, identify compounds from that as well. So then we get the overall reaction being that simple one, but a lot of the questions I've seen have had you write one of these steps, kind of like write the propagation of this or write the termination. The cool thing is did it say it in here? It's just describing it. Oh, here it is. Good. So then it describes the propagation steps and the termination steps, just like I did. Oh, there we go. Finding the traces of ethene provides good evidence that of the free radical mechanism. This is that curly arrow thing. Like I said, it's optional on this. But the single barbed would be for free radicals, and the double barbed would be if you take both electrons away. So in this case, it looks like Y is getting the electrons, so you would do both of them. You would do the double bond or the double barbed arrow. And then this is a nucleophile, and this is an electrophile. So if you have a lot of those free radicals in there, or a lot of chlorine in the mixture, you can actually get the formation of multiple chlorines in different places around there. So instead of just getting one chloromethane or a chloromethane, you could get a dichloromethane, trichloromethane, or well, this would be called carbon tetrachloride, but you could get more than one of them. And keep in mind, each time all we're doing is pulling off one of the hydrogens with one of the radicals, and then we're replacing the hydrogen with the other radical.
Mm-hmm.
Or with actually the chlorine from the Cl2. Now, alkenes, we have this double bond, so we kind of already have that those electrons available to bond because we're not saturated. Alkanes were saturated, that's why we needed the free radical process. Alkenes are not saturated, so we have kind of some extra electrons to deal with. Dun, 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 dun. And it goes in and it talks about basically alkanes versus alkenes. Again, these will burn in do a combustion reaction. Just as we said, it will have either complete combustion or incomplete combustion, which it would form the carbon monoxide. It talks about saturated and unsaturated. Then it talks about addition reactions. So we have three, looks like there are four types of reactions with the alkenes. The first one is kind of easy, that's hydrogenation. So just like halogenation was adding a halogen, hydrogenation is
It's a high.
add a
So it
hydrogen.
saturates it.
So it saturates it. Basically, it gets rid of that double bond. Now this one requires, and this was asked on one of the paper twos as well, this one requires either a nickel or a platinum catalyst and some heat.
Mhm.
So basically we need the catalyst because the hydrogen itself is going to temporarily attach itself to this catalyst. And the propane will basically come near that catalyst and it will pull those hydrogens from that catalyst in that double bond area.
So do I have to like, memorize what catalysts there can be for that or something?
To tell you the truth, I think that this is like one of the, I think you would either have to know nickel or platinum for this. Just like the other one, you have to put that HV or UV light above it.
Also, what is the? I'm not sure because of the line kind of like going through the bottom of it, but it looks like the nickel has a subscript of some sort, or maybe that's a.
It's just a
That's
comma.
Okay.
Yeah. Yeah, the lines on this printout are, yeah, it's just a comma. So halogenation here, it's kind of cool. You don't actually need the UV light. So this can actually happen in the dark. For alkanes, you need it. For alkynes, no UV needed.
For alkene.
Alkenes, yeah. Alkynes as well, but I don't think that you need to know them. So you can do that with the straight up diatomic halogen, or you can do it in an acidic solution, like the HCl or HBr.
Hmm. Hmm.
The last one I think that we will cover today, because I'm assuming you need some time to look through these, is the hydration. So a catalyst is needed to get this reaction to work, and that catalyst is a concentrated acid.
Hmm.
So this is the one that your text talks about as well, and this is the one that they're put in these notes. But basically, what happens is this the polyatomic ion starts there, and then an OH from the water, and basically you do this in a steam bath, can replace that polyatomic ion. And that's how you would form an alcohol.
Hmm.
And ethanol is a very important solvent, as you know probably, but yeah. So keep in mind that hydrogenation would make an alcohol, or add, and keep in mind what the class would be called. Do you know that this, the class is called an alcohol, but the function
Hydroxyl.
called the hydroxyl. Good. So that's the functional group is called the hydroxyl. It adds a hydroxyl group to it. And hydration hydration adds the alcohol to it, and hydrogenation adds the H's. So what that means is we can actually use that reaction to distinguish between, we can use the adding of the Br2 to distinguish between alkanes and alkenes. If we just let it sit there and it becomes colorless, meaning that all the bromine is being pulled up by whatever chemical it's in, that would tell us that we have an alkene. If there's no UV light, if it's an alkane, it will stay brown or orangish from the bromine. Does that make sense? So if you have a chemical that you're just trying to determine if it's an alkane or an alkene, basically you could add the Br2 to it. And if that Br2 does not remain in there as Br2, which gives you that color, then you know it is an alkene.
Isn't that kind of hard to do though? Because if you don't see a color change, it's
you would have to know that
alkane, but how are you?
You would have to know that you're dealing with an alkene or an alkane. So basically what this would be is, let's say that you were making two substances and you were vaporizing them off through distillation and collecting them. Maybe you see two parts on your distillation that are very close to each other where you're pulling off one and then you pull off the other one, and you needed to determine the difference between the two. If you knew one was going to be an alkene and one was going to be an alkane, then you could use this. But yeah, I mean, this doesn't say that, like, I mean, if you just put bromine in water, it's going to stay that color, right?
Well, I mean, I'm more talking about just like, how are you going to tell a color change without light? Because if you then shine a light on it to try to see if it's a color change, then it kind of ruins it.
You'd have to do, like, it's not going to be like that quick. But yeah, I get what you mean. But that's, I mean, there was a question in here, and whenever we start looking at the paper twos, we'll review that and make sure that you understand that. But basically, they're just saying that if we mix this with an alkane, there's going to be no reaction because there's absence of UV light. In the presence of UV light, then it would disappear. Now, the cool thing is, if it's an alkene, it doesn't need the UV light, so it's going to disappear anyway, right? I think that's
a typo.
Where
it says alkane on both of those, or it should say alkene in the second one. On the left side, right where your finger is.
This is right. So
below that.
This one?
It's alkane. Yeah.
This is right too.
That should be alkene.
Nope, it should be alkane. They both.
It should be?
Yep.
Oh, okay. It's presence between absence. Okay, never mind. I was missing it then.
No worries at all. This is the alkene up here. How's that?
Okay. Yeah.
Yeah. I think that's pretty good. Next time we'll do polymerization and talk about polymers. Do you know? You said you're in Spanish?
Yes.
Have you? Do you guys study like the Mayans and the Aztecs and stuff?
Well, I'm technically actually not in the class.
Oh.
I mean, I don't know. I know about the Mayans and the Aztecs if I ask me a question, I suppose. But
did you ever hear of they had a sport that they would basically they found like these fields, and the idea was to kind of kick the ball through a hoop?
Oh yeah.
Yeah.
I know that.
Was that the Aztecs or was it the Mayans or both? Do you remember?
I'm trying to think. I think it might be the Aztec.
That's what I was wanting to say too. But they actually were one of the first kind of civilizations to actually make polymers. They would take like a sap from a tree, which would become hard and brittle. And I mean, if it dried out, it would become hard and brittle, right? But what they would do is they would rub it on, they would mix that sap then with kind of the juices of a flower. I can't remember if it's called the moonflower or something like that. But basically, they would mix those two things together, and they were able to make like one of the first like rubber balls.
I think this is the name of the game. Ulamalisli.
Umalalisli. Did you type it in the chat? Yeah, you did. Ulamalisli. That's definitely, is that Aztecian? That seems Aztecian to me.
I think it is Aztec. Because like Ula, I think it derives from their word for rubber. Oh. Yeah, if you're trying to copy paste it, Zoom sometimes doesn't doesn't let you for whatever reason.
Yeah, right. Yeah. Oh, look, Olmecs. Latex from rubber trees and morning glory, not moon, morning glory. Yeah. So let me share that with you. So I always thought that was kind of neat, like, the Aztec, Olmec, and Mayan are known to have made rubber. So basically, they would use like the sap, and then mix it with morning glory vines. It's pretty cool. It wasn't until early 1900s when Goodyear made vulcanized rubber.
I believe so, yeah.
Yeah. So we're going to look at the polymers. Yeah. So next time on Tuesday, we'll look at polymerization of alkenes. We only have 2 more of these this semester. So hopefully we'll get this organic stuff out of the way then. And then
I mean, I don't know how long this takes, but if you have time now, I still have time, and I digested the previous stuff pretty well. If you want to go ahead and just move on to it.
Let's just hold off. Class, we got about 10 minutes left of class, but I want to take a little bit more time and look at this before I try to give it to you, in a sense. So it's a problem with me, not with you, unfortunately. But
dang.
Dang.
Yeah, slept in, and now you're having problems with teaching. Man.
Yeah, I took the day off almost. But go through there. What I can do is let's do this real quick if you do have time. Let me grab. Let me grab this guy. I'm gonna grab one from 2016 as well. Let's see what we've got. Boom. Boom. All right. So if we take a look, can you see this okay?
Yeah.
So if we take a look, this is in a sense how that would be tested. So identify the initiation step for this. Basically, the first step would be the bromine with the
splits into free radicals.
Free radicals.
Homolytic fission.
Homolytic. Lithic or lytic? Lytic.
I think it's lytic, yeah.
Yeah. So lytic, yep. So that and then it says 1,4-dimethyl-benzene reacts as a substituted alkane for all the structures of the two products of the overall reaction with one molecule of bromine reacts with one molecule of 1,4-dimethyl-benzene. So basically, with that, you have the benzene ring, and then you have a methyl on each end of it. Does that make sense? I don't want to write on this. I'll write on the back of here.
I get it. I mean, I can draw it real quick.
Yeah. There we go. All the structures of the two products. Well, this doesn't have anything about us having to do the propagation or anything on it. So if we have that, we basically could do the VR2. What do we need to put above this arrow?
UV light.
UV. Does it say anything about drawing? If we wanted to make sure that we could see this better, we could put the CH3 up here. Now this is kind of weird. As you, if you read through that chapter 10 of that test prep book, it has some funny things. It's like, if you were to draw, like, for example, what does it say? I'll show that in a minute. Let's finish this one. So what are we going to have here? Well, we're going to have the same structure basically, but instead of CH3, one of them will be CH2Br. And what are we forgetting? Remember, we have one Br that went here. So to make this a balanced equation, we've lost the hydrogen.
Hydrogen bromide?
Yeah. So we need the HBr on there. Benzoic acid. So you basically would have the benzene ring, and then coming off of the benzene ring, you would have carboxylic acid, which is a Cu. And notice that this one, this is showing all the atoms. So are we going to be able to use our ring structure like we did for the previous one? You have to write out every single one of those atoms. And it actually says as acting as a conjugate, it wants to know what the conjugate base of it is. So C, 2, 3, 4, 5, 6. Then we have that. Localized electrons in there, and each one of these gets an 8. Except for the top one, who gets a 2. Double bonded O. And then this normally for the benzoic acid would be that, but since it wants the conjugate base of it, as it acts as an acid, remember acids are proton donors. So which H is it going to be lost here? Well, with an acid that's not a like a HF acid or not just a halogenic acid, like if it's H2SO4, the H's that are lost are always H's that are connected to the O's. So instead of writing this one here, if we were writing
where is that?
That's the one that can be taken off.
Well, because I mean, I'm just thinking like in terms of electronegativity, like Fonkelber, O is one of the most electronegative. So wouldn't it want to hold on to the H most tightly?
This is the thing that we're dealing with. This is acting as an acid. So we want to do the conjugate base. So we know that it is removing that one. But are you asking just in general? Remember, I mean, only the strong acids ionize completely. And most of the strong acids are HCl, HBr, right? Then you've got perchloric acid and sulfuric acid. Those ionize completely, but the rest of it's all just like a kind of a balancing equilibrium game. You know, if they're not strong acids, um, something is this is losing a hydrogen. Maybe it's dissolved in water or something like that. But that H that is attached to that O, that's the one that gets taken off. Even if we were to do like sulfuric acid. Right? These are the H's. They're always attached to the O's, and they're going to be.
I mean, like, yeah, but in that case, they're both attached to O's. In the other case, with the benzoic acid, uh, there are like 1, 2, 3, 4, 5 other H's that are attached to C's, which seems to me like it would be a weaker bond, and therefore more likely that one of those would be taken off instead.
Nope. With this, with these, they're not going to be able to be pulled off. They're basically stuck to that benzene ring. And what's the, well, if it loses an H, that means it lost its positive charge. So this O then becomes negative. You remember how to find pH and POH and all that? That negative log of the pH is the hydrogen ion concentration. Negative log of the POH is the hydroxide ion concentration.
Might need to refresh myself.
That's okay. We're going to be dealing with that in the next semester with when we go back and look at acids. Formulate the equation for complete combustion of benzoic acid in oxygen. So basically, you would write this formula plus O2 and then be able to balance it. That's the last question on here. And again, that's just a balancing and combustion reaction equation. And I'm assuming that you can do the oxygen number. You remember how like sometimes that is it's a fraction and then you have to multiply everything by 2.
Yeah.
Cool. Take one more look. Oh, 3 minutes. See if I can just find it real quick. Doesn't look like I'm going to find it in time. Oh, here we go. So we take a look. We've got both propane and propene react with bromine. And this is like just one question. They're having you sit here and write the structures of them out. I'm assuming you could do that type of thing. But I just wanted to show you how this part that we discussed today is been on almost every test. So both propane and propene react with bromine. State an equation and the condition required for the reaction of 1 mole of propene with 1 mole of bromine. So again, if it's propane, what do we need on top? We need the UV light. And what are the 2 products?
Hydrogen bromide and
then the
one.
Yeah. One bromo propane. Yeah. So if we take a look, the equation for the reaction of 1 mole of propene with 1 mole of bromine, Well, instead of using the Br2 and the UV light, you would just use the Br2. And we don't have any hydrogen to pick up since it's all double, it's a double bond that we're replacing, right? Instead of plucking off a hydrogen. Keep in mind that that's going to make something like 1,2-dibromo propane. Does that make sense?
Yeah.
Because we don't have any hydrogens sitting out there, being available. State the type of each reaction with the bromine. So that would be a free radical substitution, and then electrophile addition. So that's what I mean. Like, whenever you said, I think I kind of get that other stuff, the questions that have been on that are kind of like, I would call them like memorization type of questions.
Yeah, so you have to know all the different terms involved.
Right. So again, free radical substitution is the name of when you're having a halogen react with an alkane, and then electrophile addition when you're having the halogen act, where is it? The halogen act with the alkene. And these guys again are electrophiles. Cool. I'll see you tomorrow morning for weight loss.
All right.
What's sleeping through it? Oh, for me.
Also, I suppose I'll have to make sure to be awake on my end then.
Okay. Have a great night.
All right. You too.
Bye.